idea of where we are now in our understanding of the structure of an atom. So Bohr's model is wonderful. It is simplistic, and on many, many levels, Bohr's model is completely adequate for us, and we use it. But it's missing this piece, which is thinking of an electron as a wave. Thinking of an electron not as a particle, but as energy, as a wave. So, de Broglie is another physicist, and he argued that, okay, so according to Einstein, waves can behave like particles. We can think of an electromagnetic wave as a stream of photons, and in fact, they can behave like something that has mass. So, if we can think of a wave as behaving like a particle, well, what about vice versa? Can a particle behave like a wave? So he postulated that the circumference of the orbit of an electron is actually the length of the standing wave that it is behaving like. Okay, you guys talked about standing waves in physics. But let's think about this for a moment and what that does to our thinking about the electron. So if this is a wave, okay, let's go from trough to trough. Okay, there's the wave. Now, if I say to you, where's the wave? Okay, is that the wave? Yes. 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 So the wave is everywhere at once. It's this whole thing. So if we're talking about an electron, we can't then think of the electron as being in one particular place at one particular time. We have to think of the electron as being everywhere at once. Here comes the science to try to prove that an electron can behave like a wave. So indeed, then, when these physicists performed the experiment where an electron was aimed at gold foil, it left a concentric ring pattern exactly like an X-ray. So yes, in fact, the electron was behaving or does behave like a wave. So waves act like matter, and matter acts like waves. So then again, how do you determine the position of an electron when it's behaving like a wave? Because again, waves are everywhere at once. So Heisenberg, and this kind of seems like a cop-out, but it's not. Heisenberg solved it by his uncertainty principle, claiming that it is impossible to know simultaneously both the momentum and the position of any particle with any kind of certainty. We can't know exactly how fast it's going and where it's going to be, both. We can know one or the other, but we can't know them simultaneously. This takes us to the electron cloud. model of the atom. We cannot pinpoint an electron in an atom. We cannot predict at any point in time where that electron is going to be, because it's behaving like a wave. It's everywhere at once. But we can define the region where it might be. And we call this region the atomic orbital. So we say that atomic orbitals are clouds of negative charge. And that's the way we think of electrons in atoms, as clouds of negative charge. Not as a single entity somewhere in its orbit around the nucleus, but instead its negative charge being everywhere at once. So how do we define the region where the electron might be? How do we define the atomic orbital? Well, the shape of an electron orbital, so the region where it could be, the shape of the region it might be, is determined by a wave function of that particular electron. And that has everything to do with the amount of energy that electron possesses. So Bohr was right in saying that electrons inhabit these ever-distant orbits from the nucleus, and that in order to inhabit those regions, those orbits, electrons have to have a very distinct amount of energy. They must possess a distinct amount of energy. So Bohr was right in that idea, but the last piece of this puzzle is we can't think of them as being individual entities anymore. We think of electrons as being clouds of negative charge. We know the shape of their orbital based on the wave function of the wave that electron is behaving like. All right, that's it.